Hello everybody and welcome to Operations Research video lecture, and now we are in chapter 9 of the notes Linear Programming with Spice. So this is page 37, and yes, we are studying transportation problems. So these are linear models actually, so this is not so much theory as in the previous chapters, but really a practice, and yeah, I hope that this is actually a very practical application or applications. So before going to the transportation problems, I would maybe or should be a bit of an honest. So I start with a quote. I don't remember who said this originally, but the quote goes like this: if the only tool you have is a hammer, you will start treating all your problems like a nail. Okay, so fair enough. What is the hammer here? So the hammer is the LP formulation, linear programs, and we know how to solve them, or we have this GLPK that solves linear programs for us. And yes, that's our hammer, but it's a pretty good hammer. So because of that, in this chapter we will treat these transportation problems as LPs. So it should be noted that there are other ways of thinking of them, not just on LPs, but maybe more special way, and consequently there are specialized algorithms for solving linear programs, transportation problems that are actually much more efficient, they are faster and better than this general LP algorithm that we are using. But of course those specialized, that's what they're called, specialized algorithms, they only work for these special type of transportation problems. So we are not going to consider those specialized algorithms. You can find those transportation solvers from my previous notes or just Googling if you are interested in. In this case we formulate everything as an LP. So that was a kind of general vague introduction about how we treat linear programming LPs as a hammer and turn everything into a nail, and so we can hammer it with LPs. So what are these transportation problems then? And yes, in a transportation problem, I think that the name kind of betrays it already. What one has to do, one has to ship products from ports, or let us call them later sources, to markets that we also called destinations. So there are a number of ports, and then there are a number of markets, and then there are some routes, and we have to transport the goods from the ports to markets. So what's the objective? So the objective is that we want to have the total shipping cost. So how much does it cost to transport things from the sources to the markets by different routes, and we want to make this transportation as cheap as possible. And what are the constraints? Well, there are demands for each market or destination. So we have to meet the demands. So, in other words, so what are the basic ingredients or the data of a transportation problem? So what does it consist of? So there are the supplies from the sources or ports. By the way, this is why I use the name source, because it has the same initial as supply, so S somehow relates to both of them. So each source supplies only so much of this goods that we are going to transport. Then there are demands in the destinations or markets. Again, demand and destination both start with D, that's nice. And these demands have to be met. And finally there are shipping costs or route costs. And it's assumed that this is per unit. So there is a per unit cost, meaning that the cost is linear. for transporting this and that much stuff from the sources to the destinations. Okay, let us say the same thing still, yet another differently, and mostly to fix the notation here. So this is slightly more formally what was above here. So we have n sources, n just some number, and this I goes 1 to n means that I will index the sources by I, and the source I has a supply called Si. S for supply, and these supplies are given then in a vector S. So S is a n-dimensional vector, column vector as usually we have, where S1 is the supply from the source 1, S2 is the supply from source 2, and so on. Well, in the similar way we have destinations, so let's have m of them. So the number of sources and destinations can be different, so m is just another number, and j is the index I usually use for the destinations. So each destination, call it destination number j, has a demand denoted by dj. Okay. So the demands are given by this vector d. So a column vector of size or length m, and the elements are the demands for each of the destinations. And then the final part are the shipping costs per unit, and they are then, well, this is obviously a matrix. So I is the index for the source, j is the index for the destination, and the shipping cost per unit is Cij here. So that's the cost of shipping 1 unit of the goods that we are shipping from the source I to the destination j. Okay. So this means that the shipping costs are given by a matrix C containing these elements. Alright, so what is our task then in this LP hammer way of thinking? It is to solve these kind of problems, and in order to solve them, okay, we transform the transportation problem as an LP, and once we have that, then we know how to solve LPs. So what does it mean that we have to express them in an LP form? It means that we have these problem parameters or transportation problem here. So they are S, D, and C. Okay, we have to transform these into the, well, parameters to LP. In LP we had the small c, A, B. So somehow on starting with supply, demand, and costs, we should from these construct objective function, technology matrix, and resource bounds. And how to do this? Well, we shall soon see. Just to point out, it will turn out that finding the small c and b, they are not too difficult. That's relatively straightforward. Unfortunately, finding this A, this technology matrix from this data here, that's rather complicated and tedious, as we shall soon see. Okay, this was just a general introduction of what is going on in this chapter, transportation problems, and actually also in the next chapter that is called, very unimaginatively, more transportation problems. Okay, see you in next lectures. Bye.